Hello there, my name is Hugo Vreke. I'm an assistant professor at the University Medical Center in Groningen, and I work as a consultant anesthesiologist in the General Hospital ASEAN Sint-Jan in Bruges. Today we are going to talk about how to dispose propofol properly. I have no financial conflicts of interest related to this topic. With this lecture I have two goals. First, I want to inform you on how to get rid of propofol best by explaining what happens with it afterwards. And then secondly, I want to focus on why this topic is suddenly so interesting. So, how to dispose propofol? That's the easy question because there are only three ways of getting rid of propofol. Either you give it to the patient, you throw it in the bin, or you flush it through the sink into the sewage system. If you administer it to the patient, the majority of the drug will be metabolized to propofol glucuronide and then excreted through the urine for a couple of days. So there will be some propofol glucuronide both in the hospital sewage system as well as at home. But eventually all the propofol metabolites will end up in the aquatic environment. Secondly, you could throw it in the bin, and then it depends on the country where you're from. Either in your region the waste is being incinerated, so then we have to have a look at the required temperature to make sure that propofol is broken down completely, or it is landfilled. And with a landfill system, you get a certain amount of pure propofol that will enter the environment, and over a couple of time, there will be a slow dissemination towards the aquatic system. If you enter it in the pure propofol into the sink, then of course it will go very fast into the aquatic environment. First, let's have a closer look to what happens when administering propofol to the patient. As you can see here, like I said before, propofol is generally conjugated to propofol glucuronide, but also other metabolites occur. About 66 to 88% of the active propofol will be metabolized and excreted to urine. Only less than 1% will leave the body as pure propofol. And in this study, it was clearly shown that it takes about 30 days where you still can measure some propofol glucuronide into the urine. So certainly an amount of propofol will be entering the sewage system at home and not in the hospital. So it's not enough to set a sewage treatment plant in front of the hospital to solve the propofol intoxication. One specific complication of propofol glucuronide is that if you use biological systems to clean the wastewater in a wastewater treatment plant, then we often see that in the influent a lower concentration of propofol is found compared to the effluent of the treatment plant. And that is because some biological ways of cleaning the wastewater uses bacteria, and these bacteria can sometimes reconjugate the propofol glucuronide to pure propofol. So you have to realize that eventually if you get rid of propofol without incineration, you probably will end up with pure propofol in nature. And in a minute we will have a look if that is toxic or not. If you want to avoid that, you need a wastewater treatment plant that has other techniques than biologicals. For example, ozonification is very effective, but it has some technical challenges. Although in some wastewater treatment plants it is already used. Now let's have a look what happens when we throw the propofol in the sink. In this questionnaire study, it was shown that about 5% of anesthetists tend to get rid of propofol by injecting it in the sink. About 24% throws it into the high-risk waste bag, and 70% will get rid of it by throwing it in the bin But in general, there's a lack of standardized protocols for propofol disposal, and also there's often a low awareness of what's the best option to do. So maybe it's important to have a good look what the actual concentrations are that we reach on average in the wastewaters, and there is not that much data on that. All the studies, there's a big study worldwide that looks for which drugs are mostly found in wastewater of hospitals, and the analgesics, antibiotics, contrast agents, and chemotherapies therapeutics are the most cumbersome and most concentrated drugs into the sewage system. Propofol only is found in less than 0.01% of all the pharmaceuticals, and the source is probably a combination of what is being thrown in the sink and the 1% urinary excretion by patients. Now there's a limited measurements of propofol itself. I found two studies, one in the French hospital wastewater system where they measured 3.7 to 17.5 micrograms per liter of the wastewater of pure propofol, and the toxic lowest risk concentration, this is a spoiler alert for the topic later, it is around 370 micrograms, so it's 100 to 20 times lower than the concentration considered toxic for aquatic animals. In Swedish wastewater treatment plants, which is surface water, so it's more diluted, it's not directly from a hospital but also from the city, there's only 21 nanograms per liter of propofol found. So this very dilute concentration stays away from the toxic risk zone dramatically. Okay, what happens when we throw the propofol into the bin? So the waste of a hospital is either incinerated or it is being landfilled, and that depends on the region where you're from. And here you see a list of countries that I found where mainly using landfilling procedures are incineration. It's important to learn what is the case in your region for your hospital. What temperatures are required to demolish propofol in an incinerator? Well, the flash point temperature of propofol is around 110 degrees Celsius, which is the temperature where the first vapors occur that can be ignited. But you need about 300 degrees Celsius to fully decompose propofol, although if you really want to decompose it to a mineralized state, then it requires a sustained high temperature, but the normal incinerators reach temperatures between 850 and 1100 degrees easily, which is surely enough to decompose propofol. High-risk pharmaceuticals and cytotoxics and infectious waste need a second combustion chamber with higher temperatures. And unfortunately, for propofol, despite it's not really necessary from physicochemical properties point of view, the EU and the WHO guidelines often oblige hospitals to use a high temperature incineration. Propofol will be destructed completely in a normal incinerator, but regulatory reasons often oblige us to use higher temperatures. When incineration is not available, then there are alternatives like encapsulation, chemical neutralization, or transportation to a licensed facility. Sometimes that means exportation from the country. So, of course, that has a disadvantage of needing a lot of energy, and secondly, it is not that reliable for complete destruction. Landfilling is the second best alternative, but eventually it will lead to a slow introduction of the propofol in the aquatic system. We will have a look whether this is toxic or not in a minute. It's really would be interesting to make a study in a landfill setting, what happens over time with propofol that has been stored there. So in summary, what is the best alternative if you want to get rid of propofol? Well, from an ecological standpoint, incineration is the only option that will guarantee a total elimination of propofol from the environment. But of course, it comes with a cost for greenhouse gas emissions and a potential trace pollutants if there's a suboptimal burning. So sometimes the smoke of the system needs to be treated also. But note, if the propofol is used to replace volatile agents, then the fraction of added energy is often way compensated by not using volatiles. And I added this graph to give you a feel of the magnitude of the problem, because do you realize that if an anesthetist uses desflurane for 3 weeks, being 120 hours of anesthesia, in a 2-liter fresh gas flow on average, that he emits 42,000 kilos of CO2 equivalents in heat capturing capacity for the atmosphere. This surpasses the cumulative emissions from a complete 40-year career from an anesthetist who uses TIVA alone, which ends up with less than 40,000 kilo for a complete career. Similarly, the annual leakage from piped nitrous oxide, centrally stored nitrous oxide, if you stop that, the leakage exceeds easily 1 million kilo of CO2 equivalents per year in one hospital. So that's the cumulative lifetime equivalent of 25 anesthetists who use TIVA their complete career. So by just stopping a centrally piped nitrous oxide storage and by switching from desflurane to sevoflurane or to TIVA preferably, you already have done a lot in anesthesia. So this is just to show you the average CO2 equivalent that is produced by every European citizen. If you take all the exhaust of CO2 of Europe and you divide it by the citizens, you get 6 tons per citizen per year. If you want to do total intravenous anesthesia, it's only 1 ton that you add. Of course, then we anesthetists, we produce 7 tons. Driving 30,000 kilometers in your SUV is 3 tons. If you use 1 max Sevo in minimal flow, you already give 24 tons of CO2 equivalents in heat capturing capacity to the atmosphere. 48 tons if you use it in an average of 2-liter fresh gas flow. If you add nitrous oxide, if you go in open flow, then the tonnage is rising very fast. If you add nitrous oxide in open flow, it's even more terrible. But then desflurane leads to a 600 ton per year accumulation of CO2 equivalents and heat capturing capacity. And if you go in open flow, I think that would be a criminal offense if you do that. Now that we know that incineration is the best option, but that unfortunately a lot of propofol will end up in nature in the aquatic systems, let's have a look how we can determine what the environmental hazard is of that propofol. And unfortunately that is not determined based on real in the field data. It's based on laboratory results, controlled lab conditions or model estimations. And one of the things that is being determined for every pharmaceutical is the PBT number, which is a number that consists out of 3 characteristics: the persistence of the molecule, which is the ability to resist degradation in aquatic environment; the tendency to bioaccumulate, which is the accumulation in adipose tissues of aquatic organisms; and then the toxicity, and that's really testing what concentration leads to toxic effects in aquatic organisms. Then using models, they also aim to predict how much concentration there will be available in the environment, and also what the predicted concentration is with negative effects on non-human aquatic species. The results for propofol are open access, available in, if you follow this link, AstraZeneca provides a file where you can find all the details of these testings, for example, with a number of assumptions made in this formula. They estimate that the concentration of propofol in the environment might lead up to 0.15 micrograms per liter. And according to the EMA guidelines, if you estimate the concentration being higher than 0.01 microgram per liter, then you need to do additional testing, being PBT testing, that's obliged anyway, and then determining the toxic concentration in organism. First, let's have a look at the PBT number. The persistence of propofol in nature has a negative score of 3, and that is being used in multiple review articles in the anesthesia literature, often citing each other instead of the source data, which claim that propofol is not metabolizable in nature after disposition in nature. But the original source of Brown et al. States that propofol is not metabolized in anaerobic conditions. And that is obvious because even a leaf who is perfectly biodegradable, if you put it in a peat field, it might end up 100,000 years later as a leaf because there's no oxygen. If you put it in an oxygen environment again, it's disintegrated in a couple of weeks. So the same research group also published that propofol does degrade slowly in aerobic conditions at a rate of 3% over 28 days. And luckily, the majority of the aquatic systems are aerobic conditions. Here you see the oxidation response that is taking place in natural environment in aerobic conditions. There's no hydrolysis, so indeed that is not a cause of disappearing of propofol. But another mechanism is that after 28 days it appears that the aquatic phase has got rid of 90% of the propofol, and that is due to precipitation. Propofol has a tendency to fall to the bottom. There's only a 5% uptake by sludge, so it's really precipitation that makes the aquatic systems free of propofol. But I would like to challenge with 4 arguments why I think propofol eventually will disappear from the natural environment. The disclaimer is that there are no direct studies related to propofol in the field in real natural conditions. So until more data are available, I have to honestly answer that we do not know for sure if this is the case. But as Dr. Brown already showed, that propofol does degrade at the rate of 3% in 30 days. That would mean that after 5 years there's only 40% of the original weight that remains, and after 11.8 years there's only 1/100 of that original weight. And then additional to that, we know that phenols, like propofol is also phenol, that it's common bacterial species like Pseudomonas and Acinetobacter strains. They are effectively degrading phenols, and it's even used in bioremediation of industrial sites. So it's quite, and these phenols are much more resistant to degradation than propofol. Third argument is that some plant fertilizers, they also have phenol groups or even polyphenols groups and are used for agriculture and are perfectly biodegradable. And also phenols are molecules that are abundantly available in the biological environment, even in human foods. And we know that bacterial enzymes are able to, through various pathways, to break down the phenols in hydroxylation, ring cleavage, further transformation into basic molecules. So despite the score 3 on lab tests, in natural aerobic conditions, I guess a long-lasting persistence appears unlikely, but more data is required to support my statement. The second score of the BBT is the bioaccumulation, and that is positive for propofol. It's a score 0. Although propofol is lipophilic, it appears in fish that it does not bioaccumulate, and that is because the propofol that is taken up by the fish is being conjugated just like in humans to propofol glucuronide, and then it's excreted to the urine. So there's very limited accumulation, and we are way from the concerning threshold of BCF 2000. We are in the range of 26. So it's not bioaccumulating in non-human species. Maybe some data is missing on plants, that's unsure. And then the toxicity testing of the PBT score is also negative. That is because if you give sufficient concentrations in a fish tank with a rainbow trout or with blue-gilled sunfish or Daphnia magna, you end up with certain concentrations that cause clinical effects like anxiety, loss of anxiety response, but also immature synapses that are being destructed, apoptosis, GABA-A neuron destruction, and so on. There were tests also with rats who needed 75 milligrams per kilo before they saw toxic effects. And there's a difference between chronic toxicity, but also acute toxicity could have been found in some species, but then at higher concentrations like 0.78 milligrams per liter. Now the PAC is estimated 0.15, and the low concentration that should be harmless for the most species is 370 micrograms per liter. So we end up with a positive low risk for environmental hazard of propofol. So if we fill all the results of Propofol into this flowchart of the EMA guidelines, you see that there is a low risk of ecotoxicity, mainly due to the low concentrations that are expected in the aquatic environment. In high concentrations, it would be toxic. And don't forget that in the Swedish wastewater treatment plant investigation, the concentration that was found in surface waters was only in the range of 20 nanograms per liter. So we have a big safety margin. And this is the graphical representation of the same study. Don't forget, this is a logarithmic scale. So in reality, there should be much more difference, bigger bar here at the beginning, and this would be almost invisible in this chart. So they use the logarithmic scale to allow all the molecules to be visible. What is interesting is that in this study, they found that in some cleaning systems or sewage treatment plants, the propofol concentration in the influent was lower than in the effluent. And that's because the biologically degraded propofol is returned into propofol glucuronide is returned into propofol. So how to dispose of propofol best? Well, at first you can give it to the patient, which is the intended goal, and then we will have some aquatic environment intoxication due to the reconjugation of propofol glucuronide into propofol. We can try to minimize waste by trying to maintain the same syringe and use anti-backflow valves to try to reduce the contact between patients. There is a limited amount of testing done on that, but it's still off-label use of the plastic syringes. So it's to be seen if this is acceptable in the future. Incineration is the best, but if you have a landfilling system, I do think a slow precipitation to nature will probably cause not much of a problem. I have some arguments to think that propofol is not lasting forever in nature. If you throw it in the sink, it will enter the aquatic environment too fast, and maybe that's not the way to do things properly. Now, as a final thought, I want to answer some reasons why I think this non-issue, which it actually is, suddenly becomes an issue. And that is because this topic has been brought up by the advocates of using volatiles, especially the fans of desflurane. They find an advantage in the discussion when the ecological impact of anesthesia with volatiles is blurred or is simplified. If you have a simplified image that sticks to your head, a one-liner that sticks, then you might kind of blur the seriousness of the problems. And I give you an example of a representative of a certain company who came to me and said, well, do you know that propofol is equally toxic like chemotherapy because the PBT score is equal? So would you like to have your child drinking chemotherapy? Which is, of course, no. The answer is no, but I think it's an unfair question because the PBT score is not a good reflection of the real environmental hazard, and the actual measured concentration are way below the toxic margins. And then another example of what I think is a wrong way of looking at things, that is the dichotomy between either you poison the air or either you poison the environment. And that is for two reasons wrong. First of all, it ignores the big difference in the accumulation in the greenhouse gas effect of the volatiles versus TIVA, which I have showed you in a graph before. And then secondly, it ignores the aquatoxic effects of volatiles. Because if you look at the volatiles that are metabolized in the patient, that releases around the same amount of hexafluoroisopropanoidal, which is a PFAS, a forever chemical that is never going to break down because of the very strong binding between carbon and fluor molecules. And it stays in the environment for the eternity. It will only accumulate over time. And not only that, but also the volatiles that are released in the atmosphere will release, depending on your fresh gas flow, between 6,000 and 26,000 milligram of trifluoroacetic acid, which is also a PFAS, a forever chemical that is never going to break down. And it's intoxicating the global aquatic systems day after day after day. So this is the ecotoxicity of PFAS. And I think this is something that is being ignored in the anesthesia literature. It's not in the biochemical literature, but we should be aware as anesthetists that also the volatiles are aquatoxic. Especially that with the volatiles, we have a lot of waste. We have much more waste expressed in milligrams compared to the TIVA waste that we have. In an hour of anesthesia with TIVA will maybe lead to 0.3 milligrams per hour of propofol that is being disposed on average. But for the volatiles, like I said, it's in the grams per hour that is being released, especially if you go in higher flows. Then we use a lot of desflurane or sevoflurane that is not used for the patient and is just eliminated in the atmosphere. So our research group has published several review articles that uses the quantification of both the aquatoxicity as well as the greenhouse effect of both TIVA as well as volatiles to make a list of priorities, what you can do to do an ecological correct choice with the highest impact possible. And the highest impact will first be to eliminate the central storage of nitrous oxide. If we do this in every hospital, we have contributed a massive amount of heat capturing or avoided a lot of heat capturing capacity. Then desflurane is by far the worst volatile for the ecological environment, so we should eliminate it or use it only in very specific cases. But I think it's really rare where you have cases where you would consider desflurane to be superior to sevoflurane. Stop using nitrous oxide whenever possible. And if you are able to switch to TIVA, I think it's good to have a standard approach that your standard anesthesia is TIVA, and only when you can't do otherwise, you use a little bit of volatiles. And how are we doing with reducing the desflurane use and nitrous oxide use? In this study, you saw that the greenhouse impact of the volatiles is being plotted in the y-axis, and you see that in high-income countries and upper-middle countries, the message is resonating, and you see a severe decrease in the use of desflurane with a little increase in sevoflurane. So probably many colleagues switched from desflurane to sevoflurane rather than to TIVA, but that's already a big contribution. And one of the problems is there's something that we need to monitor, that in the low-income countries, the use of desflurane as a greenhouse gas increases. We have done some simulations or some questionnaires, and we think that 10% of desflurane users in Belgium evoke 80% of the total CO2 equivalent exhaust caused by total anesthesia practice. So it would be a massive reduction if we could reduce the use of desflurane to an absolute minimum. And by this, I make a personal call to industry to consider a responsible conduct in the commercialization of desflurane and only commercialize it for very, very, very few indications. That would be the good thing to do. So, to summarize some takeaway messages: how to dispose of Propofol. Administer it, first of all, to the patient when needed by avoiding the volatiles. You might do some efforts to avoid some more waste in your Propofol also, but it's mainly because of avoiding volatiles that you did a good ecological choice. The residual Propofol that is left, you can preferably throw it in the bin, especially when it's being incinerated. But even when it's landfilled, it might be not so bad for the environment, especially when there's a very slow dissemination towards the surface waters. And I'm convinced that it's not an everlasting molecule. What you should not do is throw it in the sink, because then you increase the concentration of Propofol in the aquatic system too fast. Why is this topic suddenly so important? Because I think it's important to do a regular fact-checking to counter greenwashing attempts of people who gain some money with the volatiles. Then volatiles, you have to understand they produce much more waste drug that is not being used for the patient, much more greenhouse effect, and much more environmental pollution in the form of an accumulation of PFAS compared to TIVA. Within our professional setting, reducing the volatiles, especially desflurane and nitrous oxides, has the highest priority if we want to have an effective impact to minimize the peak global temperature rise in the next couple of decades. And of course, on the long term, we need to reduce the carbon exhaust due to the fossil fuel burning. That is more important than what we can do, but this is our profession. In our profession, this is the highest priority with the biggest impact if you want to do something for the environment. Thank you for your attention, and I urge you to look at the references and read the papers that we've published about this topic.